Okay, so this is called Agile SE Processes 201 because there was a 100 series, 101 through 106, that was done over the last 6 years, and it was about structure and architecture, fundamental enabling concepts for Agile systems and processes. Now we're moving into a different point of view where we're dealing with behavior and operation. And so this 201 is the first of an expected series that I don't think will number 6 before we're done. It may be 4 or 5. We've done some look ahead on what those might be. We have 4 metrics for agility, and they have endured now for 20 years. And I say that because we have constantly questioned throughout that 20 years all of the things we thought originally, which went through a fair amount of churn originally as we settled on things. This got settled on. It has not changed, principally because we've never found another metric that makes sense. Okay, so it stays down here. So what I'm going to do is give you, I don't want to call it a teaser, I want to call it some context. In this series, of which 201 is the first, what we are dealing with is operational behavior, principally of a process, but it can also be of a system produced by a process. There are 6 findings that we currently admit to from the Agile System Engineering Lifecycle Model Project that has gone out with a group of people in 3-day workshops to 4 different defense contractor sites doing 4 different kinds of Agile system engineering processes, some of which aren't even called Agile. One is called WAVE. Well, you probably know SAFe. There's which does have the word Agile in it. One was product line engineering, which in fact is an Agile system engineering architecture and Agile system engineering process. And the other was a traditional, well, I don't want to call it traditional at all, a variant of Scrum. At Northrop Grumman, that was principally software, that was all software oriented, whereas the other 3 workshops were hardware, software, firmware, peopleware. Okay, so in distilling what it was we got from those 4 workshops of 3 days each one, by the way, has had a paper published, which are referenced at the end of this whole webinar. In trying to distill from the case studies that were published, what were the fundamentals we saw? Right now, we claim there are 6. There may become more as we write final report and sort out some things that are somewhat on the edge of confirmed as yet, or perhaps things that we think we already always knew. They're not worth claiming as a finding for this right now. Okay, so these are the 6. I'm going to flash the first 4 past you, and then we're going to go into detail on the final 2. First one is the framework for a life cycle model for agility, and very key that we confirmed and discovered in all of this work that we did is that, unlike waterfall, Agile system engineering life cycle stages are all occurring simultaneously, asynchronously. In general, not always, but in general and most always, a product produced by an Agile system engineering process is one that's going to be so-called immortal. It's going to live for a long time. It's going to have constant upgrade, constant development, constant retirement as pieces are replaced. And so that's why we say the life cycle stages are happening all at the same time, all simultaneously. Now, in reality, They may not all be happening simultaneously at the same time, but they can be. And the interesting thing about it is this does not run afoul of the 15288 and companion standard 74748 with the 2016 update to that. If you read the text in that document, that standard and its predecessor, it very clearly states that the standards do not expect or require a sequential activation of life cycle stages. They very clearly say that asynchronous, simultaneous, recursive stage operation is quite effective. Okay, who do I hear? Do I hear something coming over the?
No,
it's the hallway. Okay. Okay, so the life cycle framework is very key. There are some a few minor but important differences. One is our claim that an Agile system engineering process has to build an Agile system, and we'll talk more about why that is true in a bit. Also, production produces and evolves. An Agile system is being built so that it can, in fact, live for a long time and be upgraded, modified, and evolved. And also in the retirement section, we no longer look at retirement as being, okay, we no longer need the system, trash it, and let's build next generation. What we're looking at now is partial, piecemeal retirement of pieces that are being replaced. And in defense environments and high security environments, you're very concerned about what happens to those pieces that were retired. Right? Okay. But that's for a later time to talk about. Another finding is what we call the general operational pattern. Sometimes we call it the ASCLCM pattern, but it's an operational pattern. It calls out three systems. They are not physical systems. You can't wrap your arms around one and walk away with it. They are, in fact, behavioral boundaries or logical boundaries within one large system with three viewpoints that you can look in at. The one on the right, which we call System 1, is the target system, the system of interest, what you're building with your process. To the immediate left of that are two boxes that deal with System 2, principally, and that's your system engineering process that's producing your system. And the two boxes on the extreme left, which we call System 3, is in our parlance known as the innovation system. It is the essence and guts of agility. It is constant awareness, constant experimentation, constant learning, constant updating of the process as System 2, and the System 1 target system. Excuse me, I need a glass of bourbon here.
Good luck on that.
I missed that.
Pass it up. Yeah, what do you think of that?
Well, it looked like bourbon. Did somebody spike that with cheese? Okay.
I better go check.
Okay.
Exactly. Let us know when.
Another set of findings we call general operational principles. We, in fact, have design principles that were discovered, a decade and a half and two ago. There are 10 of those. Now, on the operational side, we say there are 9. We've been saying that for about a year and a half, and it hasn't changed with anything we've looked at yet. Nobody has argued us away from this view or even suggested there should be an argument. That's not to say that these, as you see them today, are immortal. They haven't had as much time and testing as the earlier ones have that we did in the 90s. But basically, there's 3 categories: sensing, responding, evolving. And wonder of wonders, here comes John Boyd, looking through with observing, orienting as sensing, deciding, acting as responding. He never dealt with the concept of evolution explicitly. But if you listened, as I have, to everything he ever got recorded, which is quite extensive, he very much talks about constant evolution. So the OODA loop, which has 4 elements, is not expected to go around in the same circle constantly. Every time you go around a circle, it's expected to make use of what you learned last time and go around the circle again differently or better. Okay, anyway, these are not the subject of today's webinar, so we'll keep on. But I want to put, all of these concepts in the background because it's hard really to talk about any one of these set of findings without recognizing some interaction with the other sets of findings. What I started out showing was the circular life cycle framework. Well, a lot of what I'm going to talk about today needs that in the back of your head to understand how to make sense of it, in that you are constantly, throughout the life cycle, repeating, executing all of those stages, any of those stages at any time. Okay, the fourth general idea, general finding that I'll just flash before you today is the concept of information debt. Now, those of you who are familiar with Agile software development have heard the term technical debt. I'm going to presume that you understand what that means. And for those of you who don't, basically, it refers to shortcuts that you took in making your latest incremental delivery and that you need to get back to and fix someday or improve someday, and until such time as you do, it's called technical debt. In the workshops that we've done on system engineering operations, we came to understand it did take a while for it to glaringly hit us in the face that there's also a concept called information debt. And in a nutshell, that's when you should have done some documentation, but you didn't.
Oh, that's painful.
Yeah.
And that's,
well, it's somewhere, but not where.
Well, unfortunately, a lot of it's in people's heads.
Yeah, biological storage.
And those people leave. And the concept of the immortal system that's going to go on through many upgrade cycles is going to have a lot of flux in who the developers are. And the newer ones aren't going to know what the older ones had in their head. This became something we got poignantly aware of when we were at Lockheed Integrated Fighter Group, which will be a subject of a future seminar. But Bill Schindel makes the point. He says there are some people, a dwindling number, we hope, who still think all you have to do to get an Agile system engineering process is lift up the manifesto, slide it over, change the word from software to system, and you got it. Well, some of what comes out of software, which is very good for software, but not for system engineering, where you've got multiple disciplines in it. The software approach to agility says we favor working software over plans and documents. And for those of you who have honestly observed what actually goes on in the Agile environment, what you find is you often get working software and not documentation. And the question Bill Schindel asked is that something that has just been totally ignored in the Agile software formal practice area? And from as far as I can see, the answer is yes. Working software is not sufficient. It's maybe sufficient for that first initial development effort that gets delivered, and some of those people may hang around for another year or two to do some upgrades and evolution. When they leave, there's a big problem. Okay, so much for the preparation. Now we're going to focus on two findings: general problem space characterization and general response requirements. Other findings will be covered in subsequent. I got pizza all over my shirt.
It's a webinar.
Yeah. Okay, nobody can see
You can't
that.
see his bunny.
Let me describe
I can
it.
take a picture and we can post it.
I want to see your shirt.
Okay, so Shel Silverstein, I expect some of you grew up with
Oh, yeah.
many of his books. In any event, this is his artwork with my words. Functional focus meets customer requirements. We all, as system engineers, know we can build it. We do build it. We say it's all built. It's great. Here you are, customer. But the customer doesn't own it. The system you build is owned by the environment it goes into. And I mean owned in capital letters, as in an aggressive, predatory manner. Systems that all of a sudden get sprung on the world don't have an empty place to go fill. All that territory is taken. You put a new system out there, it's in contention over territory ownership. And the environment, in a very general sense, owns all that territory, and it's going to fight this disruption that's just come in here. I'm said about that. Okay, so I promised I'd get back to this here. You cannot have an agile system engineering or software engineering, an agile engineering process of any kind, if it doesn't build an agile product. Now, when I first said that aloud, 5 years ago, I think, got a lot of pushback from some people who thought they really understood the agile software engineering world. But they, like most everybody in that world, are totally oblivious to the fact that this is a true statement. And the reason they're oblivious is because it's the water software swims in. They use object-oriented, integrated development environments that give you a product with an agile architectural infrastructure automatically. You never have to think about it, so you're not even aware how critical it is. For them, it's not important. It's just there. Well, it's very important when we start moving into the hardware world, because there is no such thing as an object-oriented development environment. There are people who have built their own. When I say there is no such thing, what I mean is there's nothing off the shelf, commercially available, you can just go buy, mostly. But when you look at Defense Department's open system architectural concepts, that is the essence of an object-oriented environment, but they don't give you a standard and say this is what you do, these are your interfaces and such. What they do is they give you a set of values to go after, and so people who venture into this space have done so by building their own rules for the nature of their object-oriented environment, imposed upon development groups of all disciplines that have to adhere to interface standards amongst modules. So it is happening, but it's not commercially available. It has to be built. General problem that we have when, well, I want to go back to the slide. The focus of this part of the talk and the webinar is really on that right-hand side, trying to understand, the focus is on both sides. We're trying to understand the environment that the system engineering process operates in, as well as the environment that what it's going to produce has to operate in. And I want to give you some ideas on how to figure that out. And one of the best ideas, actually, is you got to figure it out. And I say that because that doesn't much happen in system engineering. We leap to solution activity and give very short shrift to an honest, objective, solution-independent evaluation of the problem space. I propose to show you some tools to do that. The general problem is that characterizing the problem space is not a well-structured problem. It's an ill-structured problem. I won't read the distinctions there, you can do that. But what is applicable in an ill-structured problem environment is a heuristic technique. You've heard the word heuristic many times. Whether or not you have a deep understanding of what it means is helped here with something that basically says it's an approach to problem solving, learning, or discovery that employs a practical method not guaranteed to be optimal or perfect, but sufficient for the immediate goals. And so what I'm going to show you are tools that are sufficient for the activities we're trying to accomplish. A little background. The observation has been made by many people that system engineering, as it is codified, talked about, taught, handbooked, standardized, doesn't deal with problem space characterization. It deals with implementation of solution. I've done a fair amount of reading in other circles, some of them in how the brain works. I have run across a number of supporting research areas that basically say we aren't wired to deal with the future. We're wired to deal with the past and form patterns of past learnings in such a way that we can immediately employ them when there's a threat to us right now. And the brain is actually hardwired with that kind of pattern detection, prediction, implementation. It's not hardwired to deal with what might happen. Let's imagine the future. It can do that, it does do that, but it's an effort of reasoning. It's not an automatic. And so it's a bit of an unnatural act to try and think and imagine a future set of situations that could be problematic. Okay, environments, project environment, process environment, product environment. I'm not going to read through these. This is an attempt to help show that there are some distinctions about those three. They're all important when you're working on a project, producing a product that has a project that's actually doing it. And there are a variety of elements in that infrastructure, and this is not pretending to shape the environments completely, but it's intended to give you some thought space. Okay, so here's the heuristic. General problem space characterization. Again, this is something that we've been using for, let's say, 3+ years at this point. It's gone through some vocabulary change, some maturation of statements on the right, as in caprice is an unknowable situation. We used to call it unpredictability, but it didn't. We needed a C. U-U-R-C was not very pronounceable, and somebody said, you know, if you could put a C there, it would be very appropriate. And it took about a year to figure out an appropriate C word. Yes, exactly.
Yeah.
That's why I say it's a very appropriate acronym. Okay, so this is a framework for thinking. That's what it is. And in the work I do in the Agile systems and process space, there are a lot of different frameworks that we use, thinking frameworks, where I say you go down through the items in this framework one at a time. Each one you put a hat on, you know, which is to say you put your caprice hat on, and you just think about the future space with unpredictableness in it. What kinds of unpredictability might come up? Brainstorming is a good way to do this. Multiple people is a good way to do this. In the end, one person has to make sense of it. It's not something you do by committee and publish what the committee says and disagrees with and agrees with. It's something that a single mind has to be able to wrap its thought processes around and say, this makes sense. But it needs a lot of input from a lot of spaces. Okay, I'm not going to read much more on this slide, because we're going to see some examples. Here's what I call high-level response needs of concern in the system engineering environment. And I've made a slide like this multiple times with different things. When you could only put 2 bullets per item on a slide, there's lots more bullets that could be there, and depending upon the audience I'm dealing with at the time, I may pick some different ones, okay? But this is notional, just to give you an idea for how things look differently under caprice than they do under uncertainty. Even though, as we've come to find through hundreds of exercises with students and with operational people, you may find the same element in more than one category. Mm-hmm. And I used to say, don't worry about it, because the idea was to think about this. There is no rightness about these things. But now I have come to say, if you actually have the same words in 2 different places, probably they came from 2 different people who were interpreting those same words differently, and you might want to tease out the different things and see if there are 2 separate issues here. Okay, so I like this flawed picture, and I like it because it graphically illustrates that you're going to build a system that's going to be surrounded by the environment, and the nature of the shape of that environment is going to dictate what you're allowed to build and get away with. What's flawed about this picture is that environment doesn't stay static. It keeps moving. So that puzzle piece in the supposed void there would have to keep changing its shape. The other problem is there is no void. When you build a system, it is hard for me to imagine that it's going to get put into an environment that's not going to rebel upon this disturbance, because that territory was owned, and now something is trying to make a claim, and there is competition for that space. Too easy to talk about is the IED technology, right? Put a new counter-IED system out there. Well, it's not welcomed. It is immediately attacked by the adversary in terms of trying to understand how do we defeat that now. We don't want it here. That's an extreme example of the situation of what happens when you put a system into an environment. I cannot think of an environment that has a void where there is absolutely no reaction. And a lot of the reaction may be political, may be cultural, may be geographic norms, and it may be technical.
Does it always have character? Could it be embraced?
Well, I will say yes, it's always adversarial, but it can also be embraced. Not necessarily by the same forces, okay? And so, in order to get away with disturbing the environment, presumably you have some embracement forces out there. Oh, that's good, I like that, I'll support that. But you're also going to have a whole bunch of people who say you stole my cheese.
Yeah, I was going to say an example of this would be Google. Customers really like it, but the cab services don't.
The who?
Cab services.
Uber.
Oh, yeah.
Disruptive.
Right. You can see on Airbnb, all of these new kinds of approaches have their counterforces that are saying, we don't want that. It disrupts our livelihood, right? Okay. Lockheed Martin, Integrated Fighter Group, the process that they employ there is what they call a tailored safe process. It is not safe off the shelf for lots of reasons, some described in the paper that's referenced there. They had to modify it heavily because they're dealing with fighter aircraft and certification and issues that SAFE doesn't deal with. It deals with a software environment. And more importantly, it deals with a commercial software environment. That's its roots. Now, today, SAFE also is evolving. Today, SAFE may say we're moving in the direction to be more inclusive, more encompassing. But the basic framework today still is something that works very well with software, doesn't work very well in a defense contracting, even if it's only software environment, because there are issues that SAFE doesn't deal with. Okay, so this is the
You're
upper.
gonna leave us hanging?
Tell you the issues. Well, imagine you're Lockheed Martin making upgrades to F-22 fighter planes. A lot of software has to be written, and that's what they do, but then they subcontract out all the devices that have to be included here, too. So they've got hardware and software that has to be dealt with. And you can't do that in 2-week cycles. That's one. Two, you've got certification and airworthiness delays that SAFE doesn't recognize in its standard framework. Three, down at the core, you're talking about Scrum process. Although I believe, down at the core, you're talking about Scrum process. What does Scrum say about documentation?
It's important, but it's not as important.
Right. And what does that really mean in practice? Yes.
It never gets done.
And how are you going to maintain an aircraft in a depot by a third-party group of people without that sustainment documentation? Now that list will go on and on. Okay. So a lot of tailoring had to happen for IFG. But what is respected at IFG is the framework concept, the basic framework that SAFE has, which recognizes there's a lot more going on than just a team or a couple teams or a bunch of teams writing software. There's 3 to 4 different levels of strategic framework importance. And as they'll say, we've got F-16s and F-22s in this program. Not to say F-16s. But one can suspect. one can suspect, since they're involved in the F-35 program, that they will be there too. And not only that, all 3 of those product lines have multiple different customers. Some international, some national. And so they have a portfolio of projects going on. Lots of different projects going on simultaneously. That's product lines. And SAFE recognizes that concept and provides a framework that gives a good initial structuring to that concept. So SAFE has a lot of value, witnessed, I think, by a lot of uptake as well, by a lot of people. But you need to be very careful that you view it as a framework guide.
Are they using it only for software, or are they using it for system development as well?
Well, they're using it for their entire system development, for all the activities that they're involved in with F-16, F-22. That's hardware and software focused.
How do they retain a 2-week sprint on a hardware?
They don't. Lockheed itself works on software. Their subcontractors work on the hardware. Now, an interesting thing that they've said is that they are unable to require an agile approach by their subcontractors by contract law.
So IFG is only a software development group?
No. IFG machine does software and hardware, but the engineering development work is mostly software. But they also specify what the hardware needs to be, select the subcontractors, give them requirements. They just don't build the hardware. They integrate the hardware.
Some of that is legal and my state built that.
Yeah, well, they made a point of saying to us in the workshop, they are unable to, they're not allowed to say to their subcontractors, here's the process you must use. Because if they do that, there is apparently, well, I'm sure there are reasons that I'm unaware of. But one of them was if they do that, then they have a certain liability if it doesn't work out. Okay, but what they have said is a number of their subcontractors working on devices have climbed on board the incremental delivery concept. Initially, they all thought it was going to be more costly. Some of them tried it and found out it cost them overall cost. And a number of them have volunteered to try to meet the 2-week or maybe a 4-week or 6-week cycle, but an incremental delivery cycle that's much more frequent than here it is at the end of the pulling of okay, so here's the curve characterization. It came out in the workshops. All 4 workshops, we went into those workshops requiring that the workshop host do some homework up front. Things they had to do. Develop the curve environment that was going to justify to us why they were doing what they were doing. Right? Now, none of them produced one that's extensive, not even one. They all tried to get away with 2 bullets under each item, because that was the example I gave. So, where these came from was in participating in the workshop, listening to the recordings multiple times after the workshop happened, trying to figure out what windmills are they tilting at here. What's that?
Those uncertainties are telling.
Yeah. Okay, so the tag that you see in front, the purpose of that tag is because later on, if this is the environment characterization, later on we're going to say, okay, so what kind of response capability do we need to deal with that? And so we're in essence going to develop response requirements. And what we want is that every response requirement we say must be done has to be justified for some reason. It needs to fulfill and address something up there in the unpredictable environment space. If it doesn't, what? Is that your favorite thing? So that's the purpose of that. This is somewhat more detailed in our discussion here and in the paper that's referenced often up there on top. Okay, so now we're going to move into what I call phase 2 of trying to figure out how to deal with the problem space, and that's what I call this reality factors. And it's a bridge between the curve environment and eventually a response situation analysis activity we're going to do to come up with response requirements. In the middle is this heuristic I call reality factors, and that's because when you sit down with the curve hat on and you go through that exercise, if you were to immediately jump into dealing with response requirements, there is a strong tendency in the system engineering world to deal with things in a very straightforward way and predictable way. And the point about reality factors is to disabuse you of the expectation that the environment will cooperate with your expectations. Reality factors are the whimsicalness that goes on all around us all the time. And there are 7 categories there. And for my students, I always put an 8th one in there called other. And some of them actually put something in that space. in my experience, these 7 areas heuristically are effective in helping you to think about this great thing I'm going to do, nobody's going to want, or nobody's going to like, or few people are going to like it. Okay, so here's an example I use in class, and I use it because it's something we've all experienced. We all think we know something about the TSA system at the airport. And so it's, as long as you weren't one of the group in TSA who designed it, it's non-controversial to you in terms of, oh no, that's not how we do, we didn't do that. But it gives some idea of the kinds of things to think about. And we're talking about a system that's going to be used by people. People don't cooperate. Sometimes they do. But if your system security, give me a break. Security doesn't work if you don't get people to cooperate with you. That's a bug, by the way, in security strategy thinking. You need to take people out of the equation. Okay, I'm not going to belabor that. That's just to give you some thought. And this slide is the actual, real reality factors that were expressed by a bunch of people in a real situation, and I'll give no attribution to it, because maybe some of them don't want some of this to be seen by some of the management. Oh.
No clue.
Okay, I'm not going to read through these things because I presume you've all been reading ahead as I've been prattling on here. Is there anything worth talking about here?
How does this relate back to your curve?
It doesn't directly. Curve is a heuristic framework that gives you one way of trying to characterize your environment. But that, in some sense, I'll say, is a sanitary way. This is the ugly way. This is the way that says, okay, what about all those people out there? Some of them are users. Some of them run your organization. Some of them are your competitors. And maybe you thought about all these when you did curve. But my experience is that you didn't. Okay, now the third element we're going to talk about is something I call response situation analysis. Abbreviated RSA in most of my teachings and writings. And it again is a heuristic framework that has 8 domains. 4 of them are proactive responses. 4 of them are reactive responses. This framework has stood the test of time now for some 20 years in hundreds of workshops, many of which did analysis, a lot of which did design of systems. You can see the 4-quadrant concept over on the right, where we have the concepts of proficiency in proactive response and proficiency in reactive response. If you're lousy at both, you got something fragile. If you're great at both, you got something agile. If you're good at one but not the other, well, you got something good, maybe. And one of my textbook examples, and I bring it up with my students a lot, is, what do you think about Intel? Where are they sitting here? When all the noise dies down, Intel is damn good at proactive proficiency. They keep running ahead of everybody. But they have been caught short a number of times by AMD in the past, who was always trying to catch up. They were very good with reactive. They got so good at reactive capability that sometimes they came to market before Intel did. with the next generation of what was coming out. This is very true. And now we see there's a similar fight going on with ARM against Intel, in that ARM is making some massively interesting, threatening to Intel, innovative moves in this space. And Intel doesn't know how to catch up. They don't have that mentality. They are not reactionary. We don't do that here. We lead the pack. Well, they're leading the pack to some place that ARM has decided isn't the right place. And a lot of other people look like they're agreeing with ARM. You know, marketplace hasn't switched yet, but it is definitely on the move. And so, one of the things you have to watch, you know, we say Agile, you need to be good at both, reactive and proactive. You need to be able to take care of opportunities effectively in an Agile way, as well as deal with threats effectively in an Agile way. If you're only good at one, you may be a leader in your industry until somebody who's good at both comes there and threatens you. Okay. Response requirements. What I have to tell my students repeatedly is when you put bullets in those 8 domains, don't think about what you have to design. That's not what's supposed to be in that space. You need to think about what does your system have to deal with when it's out there operating. You know, one of the first ones is creation. Creation is a proactive domain. And my statement to them is, what does your system have to be created day in and day out? Not what do you have to create as the designer. You know, and no matter how many times I say that, 10% of the students still put in there, well, I got to design something that does this, I got to design something that does that. The idea is to try and, again, deal with the operational environment, understanding what are the dynamics that your system has to deal with. What does your system have to be creating? Okay, I'm going to give some of the detail here, short shrift, for a number of reasons. One, Ed Carroll asked too many questions, and we're running out of time.
We're the only guy up
We got started a little late, and I got carried away. And all of this has been covered in prior webinars in much more detail than I'll go here, but this is to give you an idea for what's the difference between a proactive response and a reactive response. Reactive says you either respond effectively or you're dead or extremely crippled. Proactive says you're not forced, you're not under threat to do this, but there's an opportunity there that you can grab and run with.
It's almost like the difference between, in risk management, for example, risk versus opportunity.
A little detail on some of these things. I used to have this slide, each slide devoted to each one of these with examples from Agile software development, but they have been exposed in previous webinars for INCOSE. And these are written in a paper, a 2014 paper that talked about Agile systems engineering with a hyphen in either place. Agile systems engineering or Agile systems engineering. It's a 2-part paper. Deals with those two concepts. Details this concept. The distinguishing feature in creation is making something new or reincarnated that is not currently present during operation. It's not making a new system that never existed before. It's what is your system making constantly day in and day out. Migration is basically something that has to change your infrastructure, your interaction infrastructure. What you've got is a whole bunch of encapsulated modular resources that can be assembled to deal with response needs according to a standard set of rules about how things plug together. Well, there comes a point when you need to rethink those rules maybe allow something I never thought about before to plug in. Your home entertainment center. Didn't start out thinking about internet connectivity. But when it did add internet connectivity, it didn't give up on interfacing to my now dead uncle's 9-inch reel-to-reel tape deck. Okay. So there's what happened at IFG in terms of their response requirements on the proactive side. And as you can see on the right-hand side of each line, they're linked into the curve elements. On the left-hand side, there's a new tracking tag because eventually, when you say, and here's what we're going to do about that, here's the feature we're going to design to solve that response need, you want to link back from the feature to the response need, just like you want from the response need to the curve element. And there's more information on this in the paper that is referenced frequently here on the IFG case study that shows some of that. I'm not going to read through these concepts. Reactive, okay. I've already given the story about the difference between reactive and proactive. Correction, I wrestle with this correction with my students because what I really want them to think about is if your system of interest, and it's not true for all my students, if your system of interest is a process, system engineering as opposed to a system, because some do one or the other, the correction activities should be about your process. What's gone wrong with your process? Not about the thing it's building. And they always want a list. Well, my system broke. I got to fix it. You know, the power spiked.
Right.
Reconfiguration. You know, these things actually, I present them in order. Reconfiguration is the fourth one on the reactive side, and it's the fourth one because it's the hardest one. And it took us a long time to realize it's the hardest one. And the same thing is true on the proactive side. The fourth one there, and I forget what it is the hardest one, even though it looks like a simple one. And we came to understand that when we went out and did maturity model analysis of people who are agile to some degree or another in 24 different business practices. Some of them were beautifully agile and some of them really weren't. And what we came to learn was that people who mature over time in the 4 agile metrics do so in pretty much the same order. The first thing they focus on is how fast can I do it? And then they start working on cost. And then they start working on predictability. And then they work on expansion capability. Well, we find the same thing is true in the response domains in terms of the order of mastery that people progress through. And some are easier to do than others. Okay, so there's the IFG CS example, none of which I will discuss now because our time is almost up, but it's all, again, referenced in the paper with discussion. So getting it right. We all grew up with shall statements. If you blow one or don't have it there, you may have a dysfunctional system. That's not true with response requirements. Response requirements give you a capability that, well, I can't call it ambiguous. It gives you a capability that can be applied many different ways. And so what you really want to do in develop response requirements as opposed to feature requirements is get enough distribution in the kinds of responses you know you can handle that you can probably handle a whole bunch more that you didn't list.
Coverage.
Coverage?
Yeah.
Okay, well, I think
Reasonable coverage.
it's like putting push pins and putting a rubber band around it, and, okay, you specified 24 push pins, and they encompass a whole lot of other capability you didn't specify. If you can do this, you can do a bunch of other things too.
So are you suggesting then that, response situation analysis is to be done instead of or in addition to, or does it depend?
They're actually, if you're saying in addition to feature requirements?
Yes.
In some sense, I want to say they're unrelated. One is about to deliver.
Mm-hmm.
The other is about your capability to actually do that, given a squirrely environment. Right? So, I mean, if what you're going to deliver was determined 4 years ago with a set of response requirements and nothing changes, and you get away with delivering that and getting paid, you don't need to do response requirements. If you're working in an environment that doesn't have to respond for whatever reason, right? But if you're working, as we think virtually everyone is today, in an environment that keeps changing on you, you can't do that set of feature requirements without a lot of changes to them over time, and making changes effectively is a response requirement. And so now you start asking, how do I deal with what I know? I don't know what the changes are going to be, but I'm going to have to be able to deal with changes. How do I deal with that?
Well, looks like we're at time now.
Yeah, okay. So here's the wrap up on general response requirements as one of the findings, and these are general, they're generic. They try to be high level enough that there's got a lot of sub bullets under each one. Different environments may have noticeably different general response requirements, but this is something more than just leaving you with a blank sheet of paper and 8 categories as a framework. Is to give you some things you need to think about. Wrap up. We talked about curve. We talked about reality factors. We talked about response situation analysis. These are 3 tools that help you identify the nature of the problem space. Oh, I need to get rid of that slide. That's a duplicate. Okay, here's something very interesting that happened recently. Derek Hitchens, for those of you who probably don't know who he is one of the sanest, most comprehensive, practically oriented system engineering voices I have ever heard. He's in the UK. He's, I believe, retired now. He's got some extremely interesting videos out. But he's a fellow, and he participated in what was a very long discussion on defining what a system is. And you will see that he says, I mean, I love that he says something that supports what I'm talking about here. System engineering ignores the nature of the problem space. It's ready with a solution now. Okay, there's references that deal with all that and things to think about. You have no time to think about it. That's my plan, is to get to the end so there's no question.
Oh, yeah. You've done very well. Thank you.
Well done.